All right? Good. All right, so we're going to do that video with this audio and the PowerPoint slides. All right, so we're going to finish up chapter. If I get your attention, please. We're going to finish up chapter 2 today, and we left off talking about assigning values to variables. So let me skip ahead real quick to the portion where we left off. And we had begun to talk about strings, and we noted that strings are not part of C++ standard library. They must be brought in with an include string declarative statement. And with that library comes in a number of operators and functions, of which our chapter speaks of, and one that we already know about, and that is the plus sign concatenation. The cout is brought in with the iostream library. So here we see a set of constants, and as one would expect, constants are not variable. They're identifiers for things that do not vary, and the tradition is to capitalize their names. So here we see a number of other variables that are defined, and we see that in this case we have a declaration and an assignment statement, but we noted that we could do the same with one statement that would initialize the variables to their values. So now we're talking about expressions. So this is where we are going to have some things that are germane to our assignment that's due a week from today. So here is the syntax for an expression. And we have a variable in which the results will be stored in and an expression that will be evaluated. Again, this is very much what you would expect it to do because it's very mathematically formatted. But one should note that the evaluation of the assignment of the expression is always done first. And in effect, this is in itself an operation, an expression, a command. I should say expression, a command. It is an operator. That is an operator. That's called the assignment operator. And what it does is it takes the result of the evaluation and places the results in that variable location. So we've seen concatenation and using it in our assignment. I'm not going to go through this, but this particular set of slides shows us how concatenation can be applied to two strings and a resulting string come out. We've all used the put_to operator with the cout statement. And I noted last time at the end of lecture that the cout statement is an expression that isn't evaluated. This is an operator. This is an operator. And you might say, Professor Keelan, what does all that mean? Let me try to illustrate this to you with an example. I have a cout statement that has three parts. Everybody see that? It's just three literal constants that are part of the set of operands for an expression. You could even think of this as a traditional expression like A plus B plus C. And it's evaluated just like A plus B plus C. That's one of the reasons why the plus sign is used for concatenation. You know, I can concatenate these all together and it will come up with the same thing. But let me show you how this is evaluated. I said it's evaluated the same way that A plus B plus C is evaluated. And so how would this be evaluated? Let's just say that that was not A plus B, but 1 plus 2 plus 3. It would be evaluated in this way. 1 plus 2 would be 3. Correct? And then the 3 would be added to the 3 and we come up with 6. Right? The same way this is evaluated. This is evaluated first. Okay? So this would become that first. And the return from that expression, evaluation, would be C out. Okay? So what happens is, evaluation of that first expression would send this is to the output stream. And that means that those letters would come out in the black console box. And then that evaluation would return C out, and C out would then put 2, and the put 2 operator, the rest of this to the output stream. So it's a stream. It's placing things in the stream at the tail end. Okay? So it's like this is CS135. And it's going to continue. The next C out statement will continue to put 2 in that same stream, so forth and so on, until it encounters a end L, which pushes a end of line or return into the output stream, and it causes the cursor to come down to the next line. Do you have a question there?
Can you concatenate an integer and a main constant?
If you take an integer and you put a plus sign after it, the compiler is going to say that that's a plus sign. I mean, that's an additional sign. Okay? So, this is a good time to introduce this idea. Okay? We see A equals 1 plus 2 plus 3. We automatically know that that's a plus sign, right? If we see C out, 1 plus 2 plus 3, we know that plus sign is a what? What is it? Everybody sure it's concatenation?
Yeah.
Why is it concatenation? Because these are strings, right? And so I spoke to you about the concept of ambiguity, that even though in English we have some ambiguity which causes many, many arguments, misunderstandings. You said something and I thought you said something, but you think you said something else. Okay? We cannot have that kind of ambiguity when we're talking to the computer. It's got to be relatively clear. So what we have here, and this is a concept that I think you'll encounter in other aspects of information science, called polymorphism, or polymorphic behavior. Okay? We have inherent polymorphic behavior. We find things in context and we interpret them based upon their context. Okay? What was my expression? Oh dear. Okay? Well, we see a deer running down the hall, and I say, oh dear. Pretty much you're going to think I'm going to talk, that deer is about that deer. So within the context of what we hear, context, what's going on around us, the surroundings, we interpret things in certain ways. So we use a polymorphic behavior. Here we have a polymorphic operator. The compiler encounters that plus and looks at the context in which it is found and interprets that into a machine language instruction that says concatenate the strings. If it sees a operand that is a integer, it's going to compile that plus into a plus sign, or a plus operation, an addition operation. So you see the problem. Where was my friend that asked the question? You see the problem with that?
There are two different types.
Well, if there's no operator, you'll see this error come out almost exactly like I'm saying. There's no operator that adds an integer and a string. Ah, right? Now here's the question. You have any problem with that? That's a single quote, by the way. Wouldn't have any problem with that. Why?
It's a character. It's a character.
And what's the nature of a character? It's stored as an integer. And if you look at that table that I showed you in one of my first two slides, it's an integral data type. Integral data type. Which means it's stored as an integer. It's going to add something. I don't know what's going to get into there, but it's something to get in there. Yes?
Does it have to do like a number of I guess a number of bytes? I guess put in memory for each data type. Like I think like those like integers and characters have the same amount of storage. Where like you know what I'm saying?
Yeah, I know what you're saying, but it's not storage. It's not storage because later, hopefully in this lecture, you'll see how the computer would handle that. And we noted last week that the storage requirements for a real number or a floating point number is larger than the requirements over here, but the compiler will still know what to do with that. I'll talk about that in a second. But the real answer to your question is, how does it find out the nature of these operands? It goes to the symbol table. That literal 1, when it's encountered by the compiler, is entered into the symbol table and then it's already in there. It's a 1. It's a literal 1. It has a certain type. It's an integer. And it looks at the next operand, and if that operand does not have a compatible type or a type for which you can find an operator where it understands how to add it, it can't handle the ambiguity. You have a question here?
Yeah, I was just going to add on to that because in chapter 3, wouldn't it read it as 1 plus 1 because that's a float and that's an integer?
Well, just to get a little bit ahead of myself, what it would do is it would look at that, and the word is coerce, I heard that.
Yeah.
It would coerce which operand? Anybody sure? Let me tell you the rule. Let me tell you the rule of coercion. It's going to coerce the operand which has the lowest precision to the format of the operand with the highest precision. Did I have a hand? Were you going to answer that question back there? Okay. Yes? Okay, let's go through the steps. I don't mind getting ahead of myself. Sounds like someone's read chapter 3. Okay, look. It's going to do this. It's going to coerce that operand to be 1.0. And it's going to come up with the result 2.7. But guess what happens here? What happens if A is an integer? It's not going to round it, right? It's going to cut it off and make it into a 2. So you see how confusing this can be? And for those of you who have, I wish I had internet, I could show you the assignment 3's expression. But the assignment 3's expression is fairly complex and it requires exponentiation, integer types, and negative exponents, and so forth and so on. So, consequently, you'll have to pay attention to this coercion issue here. So, the best thing to do, if I were 2.7, is to make A a float, because that maintains the precision of my operation. Yes? Yes, sir.
I wanted to check back right quick. What would be the result if you said you used to add string 1, string 2, and string 3? What would be the
You concatenate the strings together.
so it would be 1, 2, 3? Because I just tried it and it said it wouldn't work and do it. So you can add pointers. I compiled it and it said error. You cannot add 2 pointers.
Okay, what you may not have done is include string. If you didn't include string, it doesn't know concatenations. It thinks it's plus all the time, yes.
So even though you float it, it'll still like look at 1.0.
Right, it will. This is what we call mixed mode arithmetic. I got 20 slides on this. I got you, but that's okay. This is mixed mode arithmetic. I've got an integer and a float. It's going to coerce the integer into a float, do floating point arithmetic, because it doesn't know how to do plus with an integer and a float. It only knows how to do a float or integer and integer. So what makes this even more confusing, if you aren't confused already, what happens if I have that expression? That's 1 divided by 3, not 1/3. It's the same thing. 1 divided by 3. What do you think happens? Whoever this person once said 0, that is right. It's going to call it 0.
I did understand that when I read it.
Okay, let me explain it to you. It's really a pitfall, and if you're not paying attention to the precision of your expression, you'll all fall into the pit. What happens is that is what kind of division? Integer or float division? Integer division. If you take an integer and don't get the result of integer division as an integer, not like in mathematics where think it's only 0.333, it's not. Okay? 1 divided by 3 in integer division is what? Because you can't divide 3 into 1. Okay? That's why it comes up to be 0. If you wanted this to be 1/3, good question for a quiz. If you wanted that to be 1/3 and a floating point value, 0.33333, how could you change that expression? So you could say 1.0 divided by 3. Or you could just leave it as what? 3. Because it would automatically coerce that into 3.0 for you. Yes, sir.
So why isn't like that? Like say you have an integer and a float. Why is that the float courses the integer to a float option and not the other way around, like vice versa, like the integer doesn't coerce people?
Because just as I spoke earlier in the class, and I will continue to take precision. The language is designed to do the most precise calculation it can. Okay? So if it were to take that, well, I don't have a point, take it down in precision, that's not really what you want it to do. You want it even to make up for your mistakes where you don't put 3.0 and just have a 3. So it's going to coerce the most precise. So we can do the most precise calculation that possible.
So couldn't you also do 1 divided by 3 for 3.0?
Certainly. That will work too. And for those of you who really want to get complex, we can now call a function here. Let's say we have a function called getFloat. And getFloat is defined with no operands, and all it does is defines a float n, cout, enter a float, cn, you saw this in lab, so it should be foreign to you, cn, n, and then return n. Because that's a float, because the return value from the value returning function called getFloat is a float. The compiler knows that that operand, even if it's got a 1 right here, that result from that call to that value returning function is going to be a float. What's it going to do to the 1? It's going to coerce it to a 1.0, and then whatever it gets from that execution, it's going to coerce it. It's going to return it back here as a float. The question is, if I were you, I'd say, Professor Killen, what happens if, in response to that prompt, I enter the number 3? I don't enter a float. What do you think is going to happen?
Wouldn't it force it to 3.0?
I think it would.
Because you put
Because it's saying here, I want n. Give me n from the keyboard. I type in a 3, and I want to return it as a float, and it is a float. I think it's going to coerce that input into 3.0. Okay? So now we've probably learned a lot with regard to mixing arithmetic, but I think it's appropriate because we'll need it as we move into assignment 3. So I'm going to move quickly through these slides because we've really covered a lot of this. So we know that we can put these two statements on one line in the same manner that we can say, A equals B plus C, and then D equals A plus 3. We can actually break out the expression up into 2 lines, or we can put the whole expression, where's my cursor? Or you can make my expression into an entire line because this part here returns a C out. All right, so a little bit more here about IO stream, letting us know that we do not have a IO built into input-output IO built into C++. Instead, we have to include IO stream or F stream, or I'll get into those later. Okay. So, again, the evaluation of expression. Here we have 3 constants. 2 of them are strings, and 1 of them is a character G. And if we, as you would expect, concatenate those together, we're going to come out with an output that looks like that. Now, let's move on real quick. So let's create a problem where we need to put together a chessboard. And this chessboard is 8 by 8 pattern of squares that alternate between black and white, and the upper left-hand square being white. And this is the kind of thing that you might see on an exam as a programming problem for exam. Yes, sir.
This was that previous slide. I guess I noticed, like we typically define our variables within the main, I guess, main brackets. Is that like convention or is that necessary? Like, because we'll define our constants, our main constants outside of the main function, but then like we'll define our variables within. Is that just convention or?
That's convention, and convention built from necessity. True story. I had a job for the Red Cross, and I was managing a project. We had several 100,000 lines of code, and I had like 7 or 8 programs working for me. And I tried to insist that all of those programmers define all the variables that they need inside of their main, which meant that there was no bleeding from one programmer variable names into the other. So I didn't have to enforce naming conventions. I learned the hard way. Okay? So when I put these 100,000 lines of code into one program, 2 programmers had defined a variable called M outside of main. So what happened? Conflict and error, depending on what happened was, it was on the menu system. We have menu 1 through 5, and we tested 1, we tested 2, we tested 3, we tested 4, tested 5. But what happened was the programmer who wrote option 1 had M, and the programmer who wrote option 5. So if I executed 1 and then 5, conflict. Okay? So it depended on how I executed these guys' programs, whether the conflict of M value was relevant to the output or not. So I don't want to get too complex here. The bottom line is I tested it, I fielded it, people were using the system for months, all of a sudden it happened, some error. My pager went off, moved the page from there. Now I got to run out somewhere across the country and figure out what's happening with this software. It's disaster times, Red Cross does disaster stuff. I mean, people are, they need us working. Okay? I mean, I spent nights trying to find out what was the problem, why, when, and I just happened to run across it by error. I did 1 and then 5 one night, and boom, the error popped up. So I looked at 1's code, looked at 5's code, here's that little M. So, answer your question is, if you always put in here what you need, you'll never have a conflict. We're going to talk in chapter 4 about scope. But what we're talking about here is when you define those variables outside of the main, they become global in scope, meaning they're referenceable by any function there that follows. Okay? If you define them inside main, then their scope is within those brackets, not outside. They're not visible.
And that same problem doesn't apply to when you make constants.
Well, name constants typically are, I'm sorry, that was your question. Name constants typically are defined outside of main because their intent is to be a constant value throughout all of the software. Let me give you a good example. Let's just say you're writing a program for the Department of Motor Vehicles. Not just a program, you're engineering a system. All right? And one of the named variables in there is drinking age or allowable alcohol level. Things that might change. Okay? Now, if it changes, and you're the programmer whose job it is to put this change in, and you've got all these programs and lines of code to look through to find out where the age of consent or the age of drinking or whatever it is, you're going to have a hell of a time. But if you have one place in the beginning where there's a constant, you don't have to do anything to change that constant value and then recompile it. And now everything works without a problem. Okay? It also speaks to the naming convention, so everybody should call that variable age of drinking and use your constant value for it all. So that's the use of constants for the most part. But it's also for things like pi and things whose value just going to change. All right. Any more questions? Let me move on. So let's try to produce our checkerboard. So let's look at the code that might be appropriate. But first, let's define our variable. We're going to define two constants, white and black. And you'll see that white, this should be double quotes, by the way. It's single though. These should be double quotes. You see that white is just spaces, and black is asterisks. So we're going to have something called a white row, a row beginning with a white space, and a black row, a row beginning with a black space. These are our constants. And by the way, when you're putting together your algorithms, this is a nice way to begin your algorithm. I'm not sure we have sample algorithms online yet. I think we should. But you'll see these in the slides. You should put these in your algorithm up front, and so when you're writing your program, not only will you know what variables your algorithm is going to need, you also have comments already defined that you can cut and paste into your source code from your constant values and your variable definitions. But let's move on to the code because I want to look yourself. What are we going to do in this algorithm? We're going to repeat 4 times. We're going to repeat the output 5 white rows. That's going to give us a white square, dark square, white square, dark square, white square, dark square. And then we're going to do output 5 black rows. 5 asterisks, 5 white spaces, 5 asterisks, 5 white spaces. That's going to give us the next row. And we're going to do this 4 times, giving us 4 sets of 2, or 8 rows on our checkerboard. Can everybody visualize what we're doing here? You'll see it even better when we interpret our algorithm into source code. So here's our source code. Notice we have include IOStream and string, and using namespace std, standard beginnings for programs. And we have those constants we defined earlier in our algorithm with black and white before the line of asterisks and the line of blanks. And now we have in our main, we have the string white row and the string black row. So what is our white row? A row on our checkerboard, our chessboard, where the first thing in the upper left-hand corner is a white space. So we have white black, white, black, white, black, white, black, white, black, white, black. Okay? And then we do the same thing for our black row. And now here's our checkerboard coming out with our white row, white row, white row 5 times, followed by our black row. And so our output, it doesn't show no output. All right, I'll take it from here. Okay, so it's 12.
It's actually
It's in the book.
Is it in the book?
Yeah.
Okay.
on page
Nice.
82.
Nice experiment. If you'd like to play with some code, click it back on the laptop. Write this program in Catalan. See what it looks like. See everybody glad tomorrow?